This is the screencast for section 3.1, example 8. We're going to model Dallas's population. Based on a recent census data, a logistic model this time. Now, actually, logistic models for population are more accurate than exponential. Think about the environment, think about the planet's population. If our planet grew exponentially with no limit to growth, we would eventually have so many people we wouldn't even have room to put any more on the planet. Their normal populations, they start out from zero, like a logistic model, grow because the environment is good for them, they have all the resources they need, but then the populations start to level out as the resources become maxed out, become just enough to support the amount of the population they have, the numbers that they have. Exponential growth would be completely unrealistic. So we're going to study some logistic models for population. They gave us the formula for this one. So we want to know, when will the population be a million? Well, the window for this one's a little bit easier than exponential growth because I know that my limit to growth is 1.3 million, or 1,301,000. So I'm going to make my Y max like, I don't know, 1.75 million, so 1,750,000. As far as how many years this is going to take, though, oh man, I don't know. Well, if we're talking about the year 1900, I'm thinking Dallas has increased its population and it's probably still increasing at this point, so we're going to go at least 100 years, maybe 200 years. So for my window, I made my X max 200. I put my model into Y1, my goal population in Y2. Here's my window. And then last but not least is my graph. So I can see the population really picking up. This is let's see, it starts to plateau after about 100 years, so about 2004, which is about 100 years after the year 1900, which makes sense. I mean, think about our populations now. I don't really actually know what Dallas's population is at this point, but usually these books are pretty accurate, so I'm guessing it's around 1.3 mil. So if I find my intersection, after 84 years, the population will reach a million. So since that's within the 84th year, that would be 1984. Oh, 1984. Big brother. Excellent. The now try problem number 55 throws us a little bit of a curveball. Using 20th century U.S. Census data, the population of Ohio can be modeled by, I'm going to rewrite that because that's very difficult to read as written, P of T equals 12.79. So Ohio has 12.79 people? No. Over 1 plus 2.402 e to the negative 0.0309x. That's better. Where P is the population in millions. So now we're talking about 12.79 million people. And T is the number of years since 1900. Based on this model, when was the population of Ohio 10 million? So in Y2, I'm not going to put 10 million, I'm going to put 10, because that is the number of millions of people I'm looking for. So for the purposes of this problem, I put the function in Y1, the logistic growth function that we're dealing with in Y1. In Y2, I put 10 because that's the number of million people I'm looking for. And then my window, I put, let's see, my X max, I looked at about 200 years again. I figure since we're going from the year 1900, 200 years would bring us up to 2100, and I'm thinking that Ohio is probably around 10 million people by now, so 200 years should cover it. Maybe I'm wrong. And then as far as my Y maximum, that wouldn't be in the millions. I'm looking for a Y max, or excuse me, a Y value specifically of 10, which is expressed in millions, so my Y max will be 15. Hit my graph, and I found my intersection, which would be 69.67 years, so that's looking like the year 1969, a little over halfway through. The summer of '69.